Welcome to ECC Web Seminar 2025. Today, I will present the run analysis, the production case study, best platform configuration definition during design phase. The idea of ECC Web Seminar is to present application of reliability engineering case studies that I have already performed during my professional life. Before I start, I would like to make a brief introduction about ECC. So, my name is Dr. Eduardo Calixto. I am ECC CEO and founder, Certified Reliability Professional, Certified Functional Safety Expert, and Automotive Functional Safety Professional. I have over 24 years experience in projects for oil and gas, railway, aerospace, and other 4 different organizations across the world. So here you can see some organizations that I work for, and also some of them were ECC clients. In order to have a better understanding about the concept that I introduced during the presentation, please take a look on this glossary that explains the main concept. Operation availability of time divided for total time. Production efficiency means total production divided for nominal production. Reliability is the chance of equipment or system to operate under the definition operation condition until a specific period of time. And we have different index. That's in this case here I will not present, but for you having a clear idea, we have reliability index is the percentage of subsystem or equipment that reliability impacts on system reliability. We have a failure critical index, the percentage of equipment of component system total number of failure. We have Darwin event critical index, percentage of equipment or component number of systems shutdowns. Downtime critical index, percentage of percentage of equipment or components number of system downtime, and we have production loss. That's this one I will present it here. The first step is to understand how which are the steps of run analysis methodology. In this specific case, I will also predict the production performance, not only the operation availability and reliability. So, as I already presented in different presentations, you can also see specific presentation about the run analysis methodology on ECC YouTube channel. There are 7 steps. The first step is scope definition. In this step, you need to be sure what is the scope of your analysis of the project, the boundaries, the list of equipment that will take place. Then, the second step is to collect data, prepare data. When this data are available, we have fields data, we perform what we call lifetime data analysis. We have specific presentations, also recorded video in our ECC YouTube channel about lifetime data analysis. You can go in there and get more details. In the future, I will present also a ECC Web seminar specific about lifetime data analysis. The main objective of lifetime data analysis is to define the probability density function parameters that will be inputs for the RBD model, and then also for maintainability PDF parameters concerning the repair. And in some cases, I will also include preventive maintenance task definition during a specific period of time. And then in the third step, we have the modeling, that we use the RBD modeling, reliability block diagram. Then we need to consider the time to the system will operate, the targets, and how many simulations, in case of Monte Carlo simulation that we perform in this study. Then you will go to phase 4 and perform the simulation. The simulation will produce the result, and you shows how much is the production efficiency, the operation availability, and the reliability for a specific period of time. In this case study, I use 2 softwares, the Maros from GNV and Blocksim from ReliaSoft. The objective to use these 2 softwares, that's the first one, and the time that I use it, they produce the production efficient and considering also the production profile. In this time, the Blocksim did not have all these inputs. Nowadays, they can also very well predict the production efficiency very good. but in this time not. That's why I used two software. Then of course you perform a simulation, you need to create a Monte Carlo simulation, then you get the result. And in addition of that, in the step 5, as a result of simulation, you can identify which are the most critical system and equipment that affect in our case, the platform, the gas platform performance. And you can perform some sensitivity analysis. In this study, you consider the facilities. You also consider not only the main system, the gas platform, but I also consider the facility, utilities that's in this platform, like heating, gas, and others. And then in the end, we get a conclusion. And in this study, our conclusion will define which are the platform configuration that we suggest. So as I mentioned, as a third step, we need to model the system. Basically, each equipment that have direct impact on system performance will be modeled in a series as a block, and equipment that have parallel or standby will, let's say, model in parallel. And then there are different configuration of parallel, KR of N, but we are not going deeper. We just focus on the configuration that we produce. Before starting to perform the run analysis, to collect the data and perform lifetime data analysis, and after that to perform the RBG, produce the RBG model, the RBG, we need to understand the requirement. And for the specific gas platform, there are these 3 requirements. So higher than 98% production efficiency average in 10 years, higher than 99% operation availability average in 10 years, and minimum 9% of reliability in 3 years. So the results of my simulation in the run analysis in the RBG model will demonstrate if this is achievable or not. So the first time, as I explained before, is to collect data and produce, and in the end have the parameters for failures and repairs. So here you can see, for example, the SDV valve, and we have a normal PDF. We have the mean 3.5 years, standard deviation, and 0.5 years. So I expect that this failure take place between 3 and 4 years. And when this fail take place, the repair will take between 12 hours and 4 hours. That's why we have a normal PDF for repair here for that have the mean 8 hours and the standard deviation 4 hours. And then of course here we are work on equipment level. You can see there are PDFs for compressor, for pump, for vessels, and so on. And each one has some specific parameter, PDF types of PDF. We have normal, we can have a gamma, we can have a Bible. That's mostly the result of our lifetime data analysis. And then here you can see a source of information. So that's why this was based on company data. Here, one specific very interesting point that we ECC offer nowadays, that we have our own database, and in our own database we have deeper reliability data for compressor components, pump components. Then you do not only need to assess the equipment in higher level, but you are able to include the main components from compressors such as bearing, shaft, and others, valves, as well as for a pump. So that's a great advantage, especially for the maintenance teams that need to identify inside equipment which will be the equipment that have more fails, and in the end they need to also to define the spare parts levels for each components, and that's part of a maintenance strategy. So we have all this information for all equipment that are under the scope of the analysis, and with these inputs we can decide to build the RBG. Because we, in the specific case of a gas platform, we are modeling and predicting the production, we need to know the production profile. And here one example, we have 1, 2, 3, 4, 5, 6 wells, and these wells produce a specific gas, and in the end we have the total production that go to the platform of gas. And we need to consider this profile as production gas profile. And what is very interesting here is to understand that it's starting to have high value, but in some point in the future, this gas production reduce. That means if I design a platform with a high level of redundant configuration, in the end I will not use the capacity. I will use it maybe half of the capacity. So I need to take into account this factor. And then of course, before to build the RBD, I need to build up a RBD configuration assumption list. So in this configuration assumption list here is one of the very simple that we consider that we have one of each equipment. Here we have one stage separation. So here we have, and then for this one stage of separation, this is a sub-process. Which are the equipment we have here? So we have, for example, a heater here. So if you lose this heater, I do not have any loss of production, but if I lose the separator, I have 100% loss of production. And then, for example, this second stage separator, that will be, because they cause 100% of loss, let's say that it will be modeled in series. So each equipment that have direct impact on loss of production will be modeled in series. The ones that have no effect, like this heater, they can or have no input data, or they can be excluded of the whole model. Usually I like to represent these components in RBD, but I do not put the impact of production. And then for each one of the equipment that are under the scope of the analysis, I will go forward with this configuration. Here I have two reboilers, so I can see this 100% is two reboilers in parallel. Then of course, if I lose, then I will lose 100%. And then yeah, that's the configuration. Here we have the RBD. So the RBD is very nice because they have the equipment representation. Then for production engineers or production professional, others that will read the report, they really understand what's the sequence, which are the equipment that cause a direct impact on the system. So we start to build the PDF accordingly with the list of equipment that are parts of the system, of course. And for each one of these equipment, I will have the input of reliability and maintainability data that I presented here. So for each one of them, I will have to input reliability, these two parameters and these two parameters. So that's basically the work that I have when I perform the RBD. So I have here the air compression. So I have one low pressure compressor, middle pressure gas compression, and low pressure here compressor scrub pumps, and so on. So I have only one train here represented, and that we'll see later on. That's what is the best configuration in the end, because these compressors are critical. And here, if one of these one fail, I have 100% loss of production. So we have here the real utilities. So utilities is considered also parts of the run analysis, because if some of these equipment parts of the utility, medium heating or instrument air shut down, they will shut down the whole platform. So that's why they need to be considered. So after perform this RBD analysis to model the system in RBD, we model the simulation. The simulation will take place for 10 years. So the platform performs in 10 years is 99.33% of production efficiency, operational availability 98.88%, and we have 20% of reliability. That's I make an assessment here, only consider the gas platform, and then if I add now the instrument air, the heating air, and the flare system, each one has specific production efficiency, if performance, production, operational availability, and reliability. I will see that in the end the facility, that's the platform plus utility, we have 98.14% of production efficiency, 99.97 operation availability, and 70% of reliability. So what this result means, I achieved the targets defined for production efficiency and operation availability, but the reliability is very low. And we can see here in this picture, this is a result of the blockchain software simulation, that we have high operation availability, but the reliability is starting to decrease along the time. So in 10 years, they will be close to 70%. I can have a shutdown. So how to predict that? As I mentioned, I need to include for each equipment some preventive maintenance task that's recover such reliability for 100% to stay as good as new before these failures happen. So here, for example, let's get this compressor. For each compressor I expect, I have this PDF here. Mean 3.5 years and standard deviation half a year. So the worst case, the worst case scenario, sooner that this can fail, is based on this PDF here, is 3 years. So before 3 years, if I perform a preventive maintenance in this equipment, I will bring the system to stage as new as good. So that I expect to, whenever the reliability gets in some level here close to the failure, before I have a failure. So in this case that I mentioned here, for example, 3 years for this compressor, for this ESDV, for this valve, I will perform some preventive maintenance and then bring the system to stage as good as new, and then I will be able to keep the reliability higher than expected. Another important aspect is the critical equipment, the criticality analysis. So criticality analysis, basically here we can see for in high level the global loss and downtime. So global loss is how much each subsystem they impact on the platform, loss of production and in downtime. And then here I can see the ones that's more impacting the system. And now because the reliability is low, and because of that the target is very close, is a little bit higher than 98% and 99%, 98% of production efficient, and a bit little higher than 99.99% of operation availability. The design question was, which are the configuration? I have one separation, one decompression train only with 100 capacity of each one, or I can have two separations and two decompression trains with 50% of capacity each one. So means when I lose one of this separation or decompression trains, this is separation train and this is decompression train, just to remind you. So lose one separation train means if one of these equipment here fail, that will cause total loss of this train. So the solution here, the second proposal, is have two in parallel of this separation train. That means each parallel have 50%. So that means if one of these components in one line shut down, I will lose only 50% of capacity. And the other proposal is have three, and that's the same for the recompression trains, where I have the compressors. So I have two lines with similar equipment. If I have failed in one of these equipment here, I will lose the whole train, but I will lose only 50% of capacity. And I can also have three separation trains and three decompression trains, and that's with 33% of capacity. Meaning, if I lose one of three of these lines, I will have only 33.33%, and then I have more production. But the challenge here is that I need more space in the platform, and that makes increase the operational costs concerning spare parts and maintenance. So how I decide that? I need to model this RBG, consider 2 trains and 3 trains, and compare the results. So that is the idea. So if I do that, so I will see from the first year to the 10th year, I have for different configuration, one separation train and decompression train, 2 separation trains and two decompression trains with 50% of capacity, and 3 Here is 33% of capacity. So in the end, of course, if I have two redundant separation train, two separation trains and two recompression trains, I will achieve 99.55% of production efficiency, so it's higher than what I expect. If I have three, I achieve a little bit higher, and that is the decision that the project managers and the client need to do, if they want to go in here or this will be enough. And we need to check now by this configuration what will be the operation availability, especially what will be the reliability. And that's what we've done. So we perform the simulation here, and we have this reliability. So that means and high production efficiency, high operation availability, and also higher availability. We need to, so what's happening here? Around 3 years I will perform, the idea that's around 3 years I will perform some preventive maintenance. So after 5 years here, and then the reliability gets 100%, because here when they get 63%, I will increase my reliability to 100%, and then let's go again. So in some points, because I'm performing the reliability as described in this build that I explained here before, this build here, so because in some points in time I perform preventive maintenance, I recover my reliability from my system for 100%. So I do not let my operational availability goes down. Along the time, I will perform preventive maintenance. Then that's the simulation. I just put a system impact. So here, that's what's taking place in 5 years, and then overhaul or some preventive maintenance, and then I never let my system goes below 60%. So that's why I'm showing here. And then I achieve a high, better performance with these results here by having two trains, separation trains and recompression trains that are critical equipment with 50% of capacity. And then, of course, by implementing preventive maintenance, I will not let my reliability go down and get in very low results and take the risk that to have a shutdown in the platform. So another important aspect is to see the annual production efficiency performance. So we can see in the beginning we have very high performance. I can have some losses here, and then very interesting point that's after the 5th year, the production of the well going very low. So I have overcapacity here. And then, of course, I can have some loss of production here, because this is the year that I also perform overhauling. I will perform definitely more preventive maintenance equipment, but this loss of production is better than I let some equipment shut down the platform, or it's time to have different equipment shutting down that I have a lot of case of 100% of loss of production. So, and then here you can see the production of the gas reduced. That's why in this project we did not in the end select the configuration to have 3 trains of separation and 3 trains of recompression, because after the 50th year here there is not a high demand for production, so we have overcapacity in your platform. So this case study you can find in my bestseller book, Gas and Oil Reliability Engineering, the 2nd edition. And 2nd edition, the difference between the 2nd and 1st edition, that I add much more case in the 2nd edition. And then you can see here that's in the chapter 4. Chapter 4 is a chapter dedicated for run analysis, and you can read everything they explain here in this case 4.6 4.4. So that's the case that's speaking about this platform. So if you need more information about ECC, you can go to our website. Here we can also find information about reliability, ECC reliability database. As I explained, in our database for oil and gas, onshore and offshore, we have this database. We provide access. This is an individual annual access, and you will have access to database based on our experience in different run analysis. And these databases are not only in equipment level, are in component level, I explained before. So you can visit here and get this information. Here in the papers, you will find some very interesting papers about run analysis, lifetime data analysis, reliability, even topics about artificial intelligence for maintenance 4.0 and others. Then another aspect, you can here find some information about ECC Academy training. In the second semester 2025, there will be again training for lifetime data analysis, run analysis. This aspect, I go through the training. The training will be online, and you can make ask your question and so on. And then there are another aspect in our website like career coaching. If you need some coaching for your reliability engineering career. And yeah, that's basically news. You can always check here the news. ECC books, this bestseller book here is the list of our books. We also have another books, artificial intelligence for maintenance 4.0, and we have reliability engineer runs an LCC for railway industry. We have one book for apply for safety, risk analysis and others. So you can check out the books here. Specific information about consultant service and our products, softwares. And in contacts, if you need something, yeah, just go to contact here. You can put your name and type your questions. So thanks for your attention. If you have any question, just type in our YouTube channel, and I will try to do one of these web seminars per month. That's the first of the year. Next month I will go again about in this run analysis topic, and or probably later on in lifetime data analysis. If you also have some suggestions, some specific topic here, you can go in YouTube channel where this video will be available and ask and make some comments. That will be my pleasure to share the information and make new videos. Consider that for the next web seminar. So thanks for your attention. We'll see you in the next seminar next month.